like that. I have a demo reel for this. Again, I'm going to need somebody's assistance trying to see here. Okay. It's the one that says Hunt, CryptCat. Is that it? Yes. All right. And then there's a WMV. Thank you. Okay, here I've got CryptCat. I'm going to put it in listen mode. I'm going to attach to it with the debugger. And I'm going to perform a trace once we're attached from the packet that arrives over the network. So here I'm finding the call to receive, which is a WinSock call. I'm going to set a breakpoint on receive. Then I'm going to send in a packet with CryptCat. It'll say foo bar hello world. Now that'll be encrypted over the network. Okay, so when the packet comes in, we should see an encrypted packet. And we hit our breakpoint. Now I'm just setting up a trace on arg4, which is the buffer pointer. So when the packet comes in, we'll get an encrypted packet in the memory there. It just showed up in red. Okay, so that what is that, 32 bytes of memory? That's an encrypted packet. I'm going to perform a data flow trace on that. So this data flow trace is actually tracing not just accesses to this original buffer, but every derived copy of anything taken out of the buffer, every arithmetic operation based on a value in the buffer that's then stored is also tracked. Controlled arithmetic operation, you can see that here. We're going to run this trace about 120,000 instructions in. We're gathering every single reference to every single derived value, arithmetic or direct copy from the original buffer. This right here will turn 3 days into 3 minutes, by the way, if you're reverse engineering. This is an incredibly powerful feature. It took over a year for us to develop it. So you can see the code is actually being collected there. So if you do want to interact with the code, you certainly can, even though the point of the talk is try to avoid that as much as possible. Here's a really cool block appearing on the back. I don't know if you can see that, but there's actually byte level, AL, BL, a shift left, probably related to encryption. But what I want to show you here is how we can search this graph. So I sent in foo bar hello world. Okay, so I know that was the data I sent in. You saw that it was encrypted. So let's just look for foo in the graph. Everything that was collected is being searched, all the data references, and every block that actually had a data reference in memory in one of the samples with a substring of foo has been marked for us. So let's say I can go to one of those. There's 141 samples at this location. I'm going to scroll through them real quick. You can see that up there on the upper left. And you'll see foo bar hello world. There it is. Did you see that popped in there for a second? Go back there a second. There it is. All right. So total time investment to get to this point was 6 minutes. I cut the video a lot, obviously. So 6 minutes, a couple of packets, no reverse engineering really required, and a data search. And we've identified the functions that are handling the decryption routine in this CryptCat program. Can you imagine how useful this would be in an incident response situation when you have a piece of malware you just captured off the network? Now I'll show you a really cool trick where we can do some data sampling in here repeatedly over time and actually capture all the decrypted packets. And we didn't actually have to come up with any reverse engineering to create our own decryptor. We actually let the software decrypt the packets for us. Let me go back to the slideshow. Apparently I have 2 copies running. Okay, there we go. Here's another screenshot just showing a way you could use this. So let's say that I think there's some SQL in there. I could do a regular expression search, select, and it would locate the information. Maybe the EBX register at this point in time happens to point to a string that had that substring in it. So you just saw that in the video. Now, a data tap is a slightly different idea. Once we know a location in memory where we have some processing, let's actually put something that will repeatedly sample that location again and again and again on every single packet. Remember, the packet is decrypted at that point in time. So what we're doing right here is essentially ethereal for memory. Except in this case, we're sniffing the decrypted packet as opposed to the encrypted packet. And we're letting the software do the decryption for us in the interest of time. So let's say this little purple block over here, we know it has the information we care about. Maybe the EDX register at this point in time happens to have already pulled out the secret command out of the backdoor channel of the malware and is storing it for processing. If we wanted to recover every command, all we got to do is sniff the EDX register at this point and let the software do its thing. So let's take a look at my speed break demo. Okay, once again, a little assistance. Is this one speed break? Okay, thank you. And then there's a WMV. That one? Okay, thank you. Here we go again. Let's attach to CryptCat and see what's happening. We already have a point in time where we know the decrypted data is present and pointed to by register. So we set that directly in our breakpoint address, and send in our foobar into the target program. Foobar hello world. And you can see over here on the left, the samples are starting to arrive. So this is like sniffing. It's just in memory as opposed to off the network. And you can see there's an encrypted packet, and then right there below it is the decrypted version. And as I select around, you can see the various sniffing. There's another one, encrypted, decrypted. Okay, so now I'm going to send in a whole bunch so you can see this really working. Let's say that the software is communicating with an IRC server or something, or some kind of remote commander or controller of some kind. All these packets start arriving, okay? You can see that happening there on the left. Now, we're going to go browse through there and see all the various commands that were sent in. And so we're talking about a 6-minute investment plus probably another dinking around for 5 to 10 minutes getting this speed break running. And we could put this in our report of what's going on. No disassembly required. So this particular use of active reversing, I think, is really powerful. Just as one use case is really powerful. Okay. Get back to the slides. Okay, so here I'm going to go through these relatively quickly, but here's some other things you could do. You could have a series of values, perhaps packet types, stored in a register. You could collect a whole series of those over time and do statistical analysis. For example, some of the packets will be there a lot more than others. The very unique packets, the rare ones, are probably doing things you care about. The other ones are probably control flow related. Maybe they're doing pings, or they're doing time stamps, things like that. Those things are probably not as useful. So you could see you could collect that in a whole series. It's going to be stored in a register at some point if it's a numerical value. Another thing you could do with that is actually store that information and then do a conditional trigger. So for this example, I'm going to use the World of Warcraft Warden client. 2E8, I believe, is the packet type. Is that right? 2E8, all right. Got my homie over here. You can correct me if I'm wrong. All right, so 2E8 comes in. Maybe I could trigger a trace right then. And as soon as 2E8 comes in, do a really long control flow trace. Now, I don't know if you know this, but the Warden client isn't something you can statically reverse engineer out of the WoW exe. It's sent down from the server on the fly. So it's not something I would be able to obtain unless I was doing it at runtime into the target. So now I know the packet type, I set the conditional trigger, and I get my trace. And so that'd be something like this. EAX happens to be 2E8 here, and if and only if it is, then we begin the trace, and this whole little orange region down here would be all the Warden client processing. And we could leave that in place, and every time it fires off, we could collect more and more. Proximity relevance. This is an interesting trick. Basically, if you have a particular region of memory, it stands a chance that pretty much all the functions that relate to that particular piece of data and behaviorally are going to touch it at some point. So you could use that as a clustering method. So you could actually put a node on the graph to represent the data instance and then draw lines between it and the various code, and you can actually tie together clusters of functions that statically were never connected to one another. But by the virtue that they both process the same piece of data, you know they're related to one another. So here's an example. If I have the MIME decoding class, I could put a trace on that and hopefully and quickly locate the allocation and copy routines so that I could perform a buffer overflow analysis. Freeform memory scanning is another trick. Let's just say we didn't trace foobar, but we know that we sent in foobar. We know it's probably going to be floating around in memory. So you freeform memory scan for foobar everywhere in memory. You're going to find it in more than one place. You're going to find it on the stack. You're going to find it probably in the heap a couple places. The Intel processor lets you set memory breakpoints. Those are called DR breakpoints. Under the hood, the tool can manage that for you. But the key is there's 4 of them. So if you have 4 or less, it's really easy. You just set memory breakpoints on those and do the same thing a second time, and you're going to hit the code right then when it touches it the second time. That works almost every time. If that doesn't work, you can do them 4 at a time until you get the coverage. And it doesn't take very long, and you're going to identify a cluster of code that's touching the data. And that doesn't require any tracing. That's just pure memory scanning for a substring. So, one way to do this would say, scan for my login name when I log into WoW. Let's say I'm developing a standalone third-party server, heaven forbid, and I want to be able to reverse engineer how to log in with the client so that I can emulate that. So this would be a way I could do that. I could put in my name, do the DR breakpoints, quickly identify the clusters of functions that touch it, and then and only then go in and do static reverse engineering to determine how to implement the algorithm. Okay, let's do some tracing. We saw a little hint of that in one of the previous demos. Every single instruction that's executed, if we put this processor in single step mode, can be collected. Also, we can get all the data that's in memory at the time of that. And what you also saw is that we were implementing a tracer that would actually follow the instructions and all the movement of the data and the arithmetic. That was shown in one of the demos. That's very powerful. Using that trick, we can reconstruct the entire set of classes, the class hierarchy, all their members, all their functions. Every structure that is used, we can find their members and their types as well. We can even determine whether or not they're signed or unsigned members. All of this can happen automatically. You open up a program like IDAPRO, and it doesn't tell you anything about the data structures that are being used in the program. You maybe have a plugin that tries to figure it out statically, but if those data structures are used in a running program, we can reconstruct it at runtime by only using data flow. So in the example I'm going to show you, we're going to send in a packet, and we're going to trace that packet. The packet's being cast into a data structure type, and the various members of that data structure are being referenced. I'm jumping ahead in my own slides. Let's do structure reconstruction. Okay, back here. Okay, what does that say? What's that one say? Okay, what's that one say? Speed break. That's the one I want. Okay. And is there a WMV in there, or do I got to go down one? Right there. Okay, good. Okay, we're going to set a breakpoint on the call to receive and the target. The target's going to execute and parse through the data structure, or the packet, that is, which represents a data structure. So automatically under the hood, the breakpoint's being set. We just look up where receive is, and we send in the data. And you can see the trace running on the right-hand side. So we're actually doing a data flow trace. And the only thing we care about is every reference to the data structure. The references will reveal the member types. Okay, it was actually graphed for us. So if we click the node in the graph, we should get it. All right, so here's the data structure. You can see the various offsets and their types: signed integer, unsigned short, assigned short, etc. These two at the end are really interesting. They have CC in them. That's actually some padding that was put in there by the compiler. I think Andrew actually has the source code here. Okay, there's the structure. Let's cross-reference the actual structure in the source code versus what we see in the reconstructor. And you can see we're real close. And we're actually correct. The first two fields, even though they look different in ours, that's how it was. The compiler optimized that. And the final two fields were padding placed there by the compiler. So we were able to completely and fully automatically reconstruct the data structure used by the packet at runtime. No reverse engineering of disassembled code required. Now, can you imagine how much time this could save? Actually, this particular demo deserves a shout out to Andrew, who's sitting right here, because he wrote it. Okay, back to the slides. Uh-oh, I hear people clapping. How much time I got left? Okay, thanks. Okay, so we can graph data and control flow together on the same graph, so we can see not only the data being reconstructed, but we can also see how the code touches the various members and their types. We could actually show references directly to the members, not just the class, and that can help us reverse engineer the target. So the next demo I want to show is similar to the previous one. You can